Okay, welcome folks. Welcome to week 6. Uh yeah, we're pretty far into the semester now. You're seeing lots of stuff. We've seen fundamentals of quantum mechanics, we've seen multiple types of gates, multi-qubit circuits, and today we're really going to dig into a lot of that. I am curious, how are we all feeling? You've seen a lot of things, we've thrown a lot at you. Are you feeling, excited? Are you feeling overwhelmed? A little bit of both, something completely different? What are you feeling? I'm just curious to do a little check-in before we dive into the material today. Feel free to write in the chat or just throw it out. You can unmute yourself. Always love to hear your lovely voices. Feeling great. Ooh, I like that. Feeling great. Excited. Nice. Love to to see people feeling great and excited. Seeing all sorts of different things. Ooh, of course, you've got to have some sort of superposition joke in there. Got a range, pretty easy so far. Okay, hopefully we'll heat things up for you a bit. Ooh, doubts. Hopefully some doubts about the content and not where you are in it. Ooh, curious but a bit left out. Okay, well we can chat. Yeah, my goal is for this to be a time and space for us to really dive in. So please let me know, whether it's directly or generally in the chat, just how you're doing, and if you feel like you need a moment for me to slow down or explain anything again. This is really your time to work with me and with each other. So I want to make sure that this is as effective as possible and really as fun as possible. This is pretty cool stuff. But yeah, okay. So I'm glad to hear that we're feeling excited and good overall. It's some challenging stuff at times, so no worries if you're still having some things you need to figure out. We'll do it together. Now this week, since we're kind of far in and we've settled in a bit, we're having a competition, or not a competition, but a collaboration between all the different lab groups. We have many different lab groups, and we'd love to get a collage of everybody. So if you can turn your camera on for a moment, I'm hoping to take a screenshot, get a nice picture of all of us doing some quantum things. So again, it's okay if you don't feel comfortable, if you can't, but I would love to see all your faces, even just for a moment, so we can screenshot. And again, if you don't feel comfortable being in the picture, that is totally fine. If you can't turn your camera on, totally fine, but I would love to see all your great faces. Seeing a lot of people already. This is wonderful. Yeah. Any more? Would love to see some more folks. Yeah, if we can turn our cameras on. Wonderful. All right. Okay, just took a little screenshot. So again, it would be lovely for you to keep the camera on, but if you're not able to, that's totally fine. And we will try to make sure that there's no, private information like your names and things like that given away. It's just for the fun of it. But okay, let's dive in. I see someone has their hand raised. It's yeah. Any questions?
Yes, sir. Actually, I wanted to ask about something.
Yes.
In the last homework, we were supposed to incorporate a worksheet of the Jupyter notebooks. If there is such an homework in the next week or this week, is it possible to attach the file, or tell us which file it was referring to?
Yes, so to hopefully answer all your questions there, this week there will be a notebook to do coding exercises, and there will be associated questions, multiple choice questions based on those. Those are still being uploaded and everything as we're just easing into the week, but those should be coming shortly if they are not up already. So basically you will do the notebook, the homework notebook, where you will code, and then based on your work there, you will answer a series of multiple choice questions. The multiple choice questions should more or less follow in order of the exercises you do. They may not be on every single exercise, but they will be on some of the important points. So it's a good idea to have those. But the only two things you need for homework are the notebook and the Canvas multiple choice set where you can answer questions. Yeah, and we'll probably start shifting into that way of doing homework as we get more into some heavier code. Okay, so let's dive in. Let's take a look at the material for this week. So today we are talking about the Z-gate and multi-qubit circuits. Today, we're going to, in particular, do a little bit of review. You've seen a lot of things so far. We want to make sure that you're feeling okay about it, ready to kind of start adding more pieces in. This is a great chance to ask those questions of parts that you just can't seem to get, or you don't understand why we're doing it a certain way, all of that good stuff. Then we'll talk about the Z-gate. And lastly, we'll look at multi-qubit circuits. So really taking what we've learned and basically getting more advanced, just building bigger and more complex circuits. This is really the bread and butter of the real true quantum algorithms that we will be running. Again, I already said, love to get your faces on there. Always love to see you on there. So feel free to add your video on if you haven't already. General announcements, I believe these are the same for the most part. The homework review and office hours, I believe these times are posted on Canvas as well. And really, we highly encourage everyone to go to these office hours and homework review if they have the chance and if they have any questions at all. We really don't want you feeling like you have to just struggle in isolation or anything. We're really trying to put together as many different times and places for you so that you can really get whatever help you need, have whatever conversations you need to figure this material out. So please definitely feel free to drop by for some or all of these. We've already done our picture for the day. And lastly, there's many people on the Discord server already, but if you haven't, it's a lovely place to join. Okay. This is the attendance code for the day, 6485. I will go ahead and add that in the chat as well. 6485. Code 6485. I will also add, I'll come back to this at the end and put it up just in case anyone misses it. So it's in the chat now. I'm going to keep moving on, but feel free to enter that now or at the end of the session. Again, you have up to 2 hours after the session to do it. So no worries if you can't do it quite this moment. Let's get started. First of all, let's do a little bit of review. Again, you've seen a lot. Let's talk through this. So these are the 3 general steps. This is the 3rd week in a row we're seeing this. So hopefully it's starting to get a little more comfortable. And really this describes everything we're going to do with a quantum computer. First, you create your circuit. You establish your circuit. This is one line of code in Qiskit. We will see today actually a modification of it. Step 2 is to add the gates and the measurements to the circuit. This is really where you might see the most difference, but at the end of the day, gates and measurements tend to look a certain way. After today, we will really have seen all the different types of things we could do. And from there, it's just learning more gates, learning more things to get from measurements. Lastly, there's the 3rd step, run or draw the circuit. Of course, if you're going through all this work to code up this circuit, it's really not that interesting if you don't use it for something, or at least look at it. So it's important to be able to run or draw the circuit. So first of all, I want to review how we create a circuit. It starts like this, but I'm curious if you want to throw in the chat or speak up. How do we go next? What's the next part of this line of code? Not the full line, but just what do we do next? So I've got quantum circuits. I want to make a quantum circuit. And let's say we just want 1 qubit and 1 classical bit. Yeah, 2 numbers, nice. Yeah, I'm seeing it. Ooh, yeah, okay. So yeah, we got it. So 1, the number of qubits in your circuit. It's easy to get mixed up with this, but always remember in Qiskit, quantum things come first. It's a quantum coding language anyway, or library. So quantum bits, qubits go first, how many you want. And then classical bits go next. So one qubit, 1 classical bit, where the symbols here below are what we typically draw. 1 line for a qubit, 2 lines for a classical bit. It's just the convention, just one way to tell the difference. Now we also have gates. These are some of the gates that we have seen, the X and the H gate so far. Today we'll add several more to this, the Z and the CX. We'll see those as we come, but basically this is the syntax, pretty straightforward. The thing that usually tricks me up the most is just remembering lowercase versus uppercase. It's always lowercase in code. Okay. Now, in step 2, we can also measure. That's really kind of the interesting part, right? If you run all of this code and run all of these gates, it's not all that interesting unless you actually get something from it. We need to be able to measure to do that. Here is how you do this. You specify which bit you want to measure and which bit you want to store it in. In particular, the first location, the first number, is the index of the qubit you want to measure. Just like creating a circuit, the qubits go first. So this is the index of the qubit, so qubit 0, as you see here. And then the second number is the classical bit that you want to store the result in. The classical bit that you want to store the result in. So it's the index, so we start at 0, even though we have 1 of each. Lastly, we have the third step there, and we've really seen many ways to do this. And in fact, there are many more that we will end up seeing and some that we won't. But these are the main ones we've seen so far. We can use the first one if we want to just see the circuit diagram. It's often helpful to see what diagram you have to make sure that your code works correctly, is doing what you expect, and to refer back to. The diagram is meant to be helpful a lot more than looking at many lines of code, for instance. But sometimes you want to really see what happens in it. And so you can run, or really it's a simulation, to see the block sphere rotation. This is really helpful and a really beautiful tool. But the honest truth is, as soon as you have more than 1 qubit, it just is not going to be that helpful generally. So it's really helpful for understanding what's happening to individual qubits, but things like entanglement are actually notoriously very difficult to visualize here. So this is a tool that we've seen. It's helpful for single qubits, but as we move on, we're going to need more ways to interact with our circuit and understand it. Lastly, the way to do that is to simulate and get measurement results out. So we can't see everything that's happening, but at least we can see what we get out when we measure it. We're going to provide this code for now, although today we'll dig in a little bit because we don't want you just looking at code and having no idea what it does. First of all, to draw a circuit, such as getting an output on the right, you just say qc.draw, where qc is the name of the variable, or the variable name of the quantum circuit you have. So you draw here, and then this will create some pretty thing like this, or in IQX, you'll get all sorts of colors and all of that as well, which is very nice. And it's just a way to get a visual, right? It's much easier to visualize things than to see many lines of code. We can visualize the transition to see the rotation on the block sphere with this. Again, we've been seeing this for a few weeks now. This is a very handy tool to use. But this is the new bit that we just saw last week, and we will continue to see more and more. This is to really run your circuit. It's a simulation for now to get measurement results, right? To get something like this, to plot a histogram in particular, and get a sense of what's the probability of getting one result versus the other. Okay. Now, this is the code to simulate that we've been using. Last week, we just gave it to you, said, don't worry about it, don't question it, it's just what it is. And to be honest, we're not going to dive too deeply in, because of all the things we're throwing at you, of all the things you're learning, it's honestly not as important. This is something that is not as fundamental. It's something that could change a lot. But nonetheless, we want to give you some sense of what this code is doing. So we'll walk through it a little quickly. First of all, these first two lines create the type of simulator you want. This tells your code, hey, I want to get the QxQ simulator in particular. You can think of it as like, it's called a backend. You can think of it as like going out back to get this simulator. If we wanted, we could change this to other simulators that are available. We'll see some options as we go. And then you actually run it. Note that this first line has nothing to do with the quantum circuit you made. It just says what simulator you want to use. QxQ provides many different simulators. This is the one we're using for now. The reason we use this for now is that it is the most flexible for relatively small circuits. The particular number is 32 qubits or fewer. That's just a very particular specification, but generally for relatively small circuits, this is the most general, the most flexible. So this is the one we like to start with, but there are many other ones you could use for if you want to simulate with error models, like there's errors on your computer, on your quantum computer, and you want to see how that will affect the outcomes, or you want to do it more efficiently for certain circuits. There are some ways some tricks we can do to pull that off. For now, QxQ is the most general, so we'll use it. Then you can actually run the job. Again, here is where you actually specify the quantum circuit you're using. So if you called your quantum circuit something different, then you would change this part. You specify what you want to use, which simulator you want to use to execute this circuit. And then SHOTS is a kind of experimental language or experimental physics lingo for number of measurements. So SHOTS equals 1024, says that we will rerun this circuit 1024 times and get the measurement results for each time. You could change this number to be way fewer, way small, way larger, whatever you like. But 1024 tends to be a pretty nice, steady number. It's big enough to get a lot of results and kind of get something meaningful, but not so big that it'll take a really long time to run. Next, we actually want to get the results of this. So up above, we've executed it, we've run our quantum circuit. Then we want to get the result of this back. What actually happened? What were the 1024 results that we got? And then in particular, we unpack this to get the counts. Specifically, that means the number of each result. So for instance, if you're measuring 1 qubit, you're getting 0 or 1. This is the count of how many zeros you got and the count of how many ones you got. And lastly, we want to plot it. It's not very helpful to just look at a bunch of numbers. Let's actually plot it. So this part actually plots the histogram. So the histogram is really just our way of seeing the data or visualizing the data, but most of the work is actually done up above. And this is one of many tools that QxQ provides in order to be able to visualize measurement results and other things. Okay. So again, you are not responsible for that code. We will always provide it for you, at least for now. But I just wanted to make sure that you actually knew a little bit of what was going on there. I also want to point out that there are a lot of simulators. For instance, here are several different simulators, many of the simulators provided by QxQ. These simulators, generally simulators, are really good for running complicated circuits that you want to do quickly and reliably. As in, you want to be guaranteed that the results are correct in some deep sense, that you're not getting all sorts of errors that you would get from running a real computer, which happens with both classical and quantum computers, actually. On the other hand, you can also build in all sorts of physics to this. So you can actually add in different errors on purpose and see how they would affect your results. So simulators are really good for testing out your ideas, testing out your quantum circuits and algorithms before you actually run them on a real quantum computer. That being said, of course, this is a quantum computing course. We want to see this in action. This is the real deal. We will see these soon. I promise we're getting very close to using them. And it won't be that huge a jump, actually. But for now, the number of options with these, the number of parameters we can set, the size of the circuits are only beginning to grow. There's not as many options as with simulators. For instance, the largest number of qubits you could use with a simulator with Qiskit is 5,000. With a quantum computer, a real one, it's 127 with IBM. And even that we don't all have access to all the time. It's closer to 5 or 7, maybe 27. Compared to 5,000 though, it's quite a difference. Okay, so that was some background, but let's actually go and do some practice. I would love for everyone to go to the IQX, the quantum experience, and join there with your notebook. I will also share the notebook in the chat. And then we will go through these parts together. So go ahead to the chat here, or sorry, the notebook here. I will share it in here again for anyone that didn't happen to get it. Again, these are always available on Canvas as well. And while you're getting this loaded, let me know if you have any problems getting set up. I also really appreciate that folks are pretty good about helping each other in this group. I really appreciate that. You seem to really help each other out when you notice there's issues. So please feel free to keep doing that. One thing I want to point out, this week we have provided a cheat sheet of sorts. So if you click that link, it'll bring up this cheat sheet. This is meant to just be a list of the handy things that we've learned, really broken down to the basic pieces. So it doesn't exactly tell you how to run some complicated quantum algorithm, but it tells you each of the pieces that we have seen specifically and what you can do with them. So if you're ever lost or you're just forgetting, this is a great thing to look at. Yes, do we have questions?
Yes, sir. Sir, actually, when we click on that link, it's asking for you don't have access to this sheet. You need to ask for access.
I will update the permissions on that. I believe, yeah, let's see. Let's see if I can update the permissions. Okay, try reloading the page now and let me know if that helps. Are people able to get access? Ooh, I see people popping on. Awesome. Okay, I see some people hopping on, so hopefully that's working now. This is going to be really handy, and we may in fact actually build it up as we go. Please, please, please always refer back to this. There's no point in stressing out and spending hours trying to memorize something. You have access. It's far more important that you can just look it up and know how to use it as opposed to just memorizing what it says. Okay, let's go through. First of all, we want to import all our parts from Qiskit. So let's go through and run part 0 here. Again, this is just running through, importing all our libraries. And more importantly, let's now go through the review section. So we're going to do this together. For sake of time, I'm going to fill in these lines and I would love for you to follow along, but please let me know if you have any questions or other approaches to it that you would want to take. So for the first exercise, we want to create and draw a 1-qubit circuit with 1 X gate. So we want to create a 1-qubit circuit. Well, that's quantum circuit of 1. That's it. That's a 1-qubit circuit for you. And then we want to apply an X gate. and then the draw has already been provided for you. When you do this, you can see the result. Again, it's not very interesting if you don't draw it. Drawing confirms that you actually wrote code that does what you want it to. Then we want to simulate this using the visualize transition function. This has already been provided for you. A lovely TA pointed out that we can actually make this load much faster if we reduce the number of frames per gate. This is a special parameter that basically just makes it move a little faster, as you'll see. So it does this. Basically, now it's only going through 5 different points as opposed to many, many points and creating a smooth line. The important point being that you can see the effects of this. So I'll loop through and you can see this running. Hopefully it's running a little faster for folks. Okay. How are we doing so far? So that's exercise 1. This is all stuff we've seen, but it's okay if you're still feeling a little lost on it, but now is definitely the time to ask any questions. How are we feeling on this? Any questions? Okay. Let's go to exercise 2 then. So exercise 2, let's create and draw a 1-qubit circuit with 2 X gates and a measurement. Now, because we need to make a measurement, we want 1 qubit and 1 classical bit. We need to store the result of our measurement somewhere. Anytime you see measurement, you should think, oh, I need classical bits. So measurement means we need classical bits with our quantum bits. Now, the 2 X gates have actually been provided for you. No need to do work there, but we also need to complete this line. We need to make the proper measurement. So we specify the qubit index first, that's 0, and then the classical bit index, 0. And then we can run this. And now we see a nice circuit. It's measured down here, all good. Now let's actually simulate this. When we run this, we get out the histogram that says out of 1,024 measurements, as we discussed, 1,024 of them were in the 0 state. In other words, 100% of the results were in the 0 state. That should make sense if you walk through these gates, and I would encourage you to go back over these and see why that makes sense. But these are the expected results. So that's just a little warm up just to see all the different things that we've looked at so far. I'm actually going to move now back to this, to our slides, and just see, do we have any questions? Do we have questions on that? So we've been seeing that a few weeks. I really want to make sure that if you're feeling unsure about this, if you're feeling like left behind here, I want you to know that you can let me know that, and I would love to hear that so that we can make sure you're caught up here. Any questions on this? Okay. Okay, seem to be feeling all right. Then let's move on to the Z gate. This is a new gate, one of many that we will see, but another important one. So as we saw in lecture, the Z gate is a rotation by 180 degrees around the Z axis. Again, the Z axis is typically what we point up and down with. It's the one with the 0 on top and the 1 on bottom. So more or less, it doesn't do anything to the 0 or 1 states besides this kind of strange -1. Again, as discussed in lecture, that's a phase. We will see what that means and the effects of it later on. We get slightly more interesting results with the plus and minus states because you basically have this arrow pointed out, your state pointed out, and it rotates around, much like a carousel. So the plus state rotates over to the minus, and the minus state rotates over to the plus state. In Qiskit, it's just .z applied to whatever gate you want. It looks, or qubit you want. It looks exactly like the X and H gate so far. The only difference is, of course, the name is Z. And again, lowercase z. So this shouldn't be too difficult if you're feeling all right so far. So why don't we just go ahead and jump to the exercises. We'll do 1 through 3 together just to see some different things, and then you can do a couple on your own. So let's run through these first. So jumped around. So exercise 1, let's create and draw a 1-qubit circuit with one Z gate, So again, I'd love for you to follow along. QC dot, now instead of X or H like we've had, it's just a Z. The point of Qiskit is to make these quantum gates that can be very complicated in their effects easy to use, right? This is just changing out X or H for Z. Exercise 2, we will do the exact same thing, but now we'll visualize it. What I typically do when I have code like this, honestly, is I copy and paste it. Now, it's really important that you really think about what you're doing. So I would highly encourage you to really type this out. Think about, okay, I'm creating a quantum circuit with 1 qubit. I'm applying the Z gate to the 0th qubit. But just know that in the long run, that's an okay method. Now let's see it in action. Not very exciting. It's rotating in place, just spinning in place. So we really don't see much action here. It really just leaves the 0 state alone fundamentally. But nonetheless, now we've confirmed it. Now let's look at exercise 3. Here we want to create and draw a 1-qubit circuit with one gate applied, with the X gate applied first and then the Z gate with a measurement at the end. So first of all, we need a 1-qubit circuit, quantum circuit of 1, but we need to be careful because there's measurements at the end. Anytime you have measurements, you need classical bits to store them. So 1, 1. Then we need to apply an X gate and a Z gate. Again, it's really not all that different. It's just specifying which gate you want. And then we need to measure. So 0, 0, no different than before. And we get out this nice result where now we have an X and a Z. Now let's actually simulate this and see what happens. So again, not a whole lot. The X moves it to 1, the Z gate spins it around and does give it a little phase. But at the end of the day, when you measure, phase is a purely quantum mechanical thing. We don't get that. We just see 1. It's 1 or it's 0. There's no sense of phase in classical physics. There's no phase with classical bits. So we just get 1 out. Okay. Now, I would love for you to take some time to do exercises 4 and 5 on your own. Feel free to ask any questions, but I want to give you a chance to code some things up. So go through exercises 4 and 5 now. Take a couple minutes to do that. Exercises 4 and 5 in part 2. And let me know if you have any questions. Yep, I can go back to exercise 2, no problem. Let's look here. Yeah, I'm glad to answer any questions about that. Okay. The one after, exercise 3. Yep. Let me know if you want to see the measurements. No problem. Okay. So exercise 4, I'm going to start reviewing now. If you're still wrapping up, that's okay. But let's go through these. Exercise 4, create and draw a 1-qubit circuit with gates applied in the order listed below with a measurement at the end. Immediately I read the word measurement and I think, oh, I will need a classical bit. Then simulate the measurement result using QASM. That code is provided. So we need to create our quantum circuit, but again, we will measure, so we need that classical bit. We apply an H gate and then a Z gate. It's as simple as just reading it off and making sure you're in lowercase. And then we want to measure, well, it's the 0th qubit measured and stored to the 0th classical bit. Let's draw this just to make sure that it matches up with what we want and to get a nice visual. And then we'll run the code provided and we get a nice 50-50 split. Again, if you re-ram this, you would get different results most of the time. Unless I forget exactly who it was last time, but someone had the same results most of the time, which was pretty impressive. But here we're getting different results most of the time, but roughly you can see it's about a 50-50 split. We have a superposition afterwards, after all. All right, now exercise 5. Similarly, we're going to need a quantum circuit with 1 qubit and 1 classical bit. We will apply the H gate, the Z gate, and the X gate. I'm also going to zoom in just so you can see that a little better. I know that can be a little hard to read sometimes. And then we want to measure. And lastly, let's draw that just to confirm. And this is what we should get out. H, Z, and then X, and measure. 1, 2, 3, measure. Now let's see what the results actually look like. We'll probably have to zoom out a bit for that. Again, it's roughly 50-50. 50-50. The H gate, anytime you see that, you should immediately think, ooh, superposition. The H gate, the Hadamard, that is the superposition creator. So we get a superposition. That should not be a surprise given that we have an H gate in there. Okay, so any questions on that part? Any questions on this? Okay, beautiful. So hopefully the Z gate is, yes, please.
So can we run the QASM simulator and the draw function at the same time? Like, for example, in the same piece.
Yeah, it's a great question. The answer is you can, but you will only see one at a time. So that's just a particular quirk of this. I can show what would happen. Basically, the question is, if I do this, as in, why do we always have it in a separate cell? If I do this, notice that we only get the histogram out. So it's important that they have their own cells. That's just a very particular Python notebook thing that has nothing to do with Qiskit or with quantum computing or anything. But yeah, so usually we draw separately and do this. But I do feel it's very important to draw your circuit so you can see it in action, and then, or see what it looks like, and then see it in action using the QASM simulator. Yeah, it's a good question. Okay, so again, hopefully the Z gate isn't too difficult if you're feeling all right with the rest. It's really not that different. Where things might start getting a little different is multi-qubit circuits. So before I move on, I just want to last check any questions.
Excuse me, sir.
Yes, please.
So similarly, like last week, I'm getting all the same answers. Are you sure it's not some defect and it's just random?
That's a very interesting result. For now, I'm going to say it's not a problem. You're probably just getting the result that is exactly predicted as opposed to something closer to what you would actually get. So I don't think there's anything wrong with the results, so to speak. But I'm going to actually look into that, and I'll try to bring that up next week to see if there's any reason why that might be happening for you specifically. But again, I doubt that you are getting the wrong results. I think you are just getting very consistent results, which are never a bad thing. But we'd like to add a little more randomness if we can.
Okay, sir. Thank you.
Yeah, no problem. All right, let's look at multi-qubit circuits. So there's only a few things, 2 in particular, that we need to change when we want to create a multi-qubit circuit. Everything we have seen so far is single qubit, but now we want more than one. There's actually only a couple small things. One, when we initialize the quantum circuit, we need to do that with the desired number of qubits and classical bits. So far, we've been saying 1 qubit and 1 classical bit every single time. We just need to change that. And 2, when we measure the qubits that we're interested in, we need to use all of the correct indices. This is a little more complicated, but it's still very closely related to what we've seen. So let's dive in. First of all, this is what we've seen so far, right? QC equals quantum circuit of 1, 1, the number of qubits, classical bits. It's always been 1. 2. We could have quantum circuit of 2, 2. This creates a 2 qubit, 2 classical bit circuit. It's really not that different. It might take a little bit of getting used to, and I know that the 1, 1 was already somewhat new, but basically you specify how many qubits you want, and it can be any number, 1, 2, anything like that, and the number of classical bits. For what it's worth, it's just a side note, they don't have to be the same number. So we have used the same number the whole time, but they don't actually have to be. There are some cases where you will run a really complicated quantum algorithm with many, many qubits, but you actually only care about the result of 1 qubit, for instance. Maybe you have some entangled qubits in some very complicated state, and you can actually get a lot of information from just one of them. So this is actually something you will probably see down the road from time to time. So it's just important to know that the number of qubits and classical bits do not need to be the same. Now, if we want to measure, it's a little more complicated, but I promise it's still basically the same thing. Here, we now use a list of all the indices we want, where I'm using indices as the plural of index. So we have a list of the qubits that you want to measure. So again, qubits come first. So we had 0 before, but maybe we now want the 0 and the 1 qubit to measure. And then we have a list of the classical bits you want to store the results in. Okay. So in particular, this is saying measure qubits 0 and 1, store the result of measuring qubit 0 in the classical bit 0, and store the result of measuring qubit 1 in the classical bit 1. That's how we read this. It'll look the same every single time, no matter how we change these numbers or add them. And in fact, we're going to look at some examples now to see how this can change and what stays the same. So let's take this circuit, for example. I'm going to walk through the answer to this of how we would create the measurements shown below. And then we'll see a few other examples that I want you to kind of give your opinion on. So for this one, we would use the same command that we saw on the previous slide. Measure of 0, 1, 0, 1. These square brackets are very important, these here. And basically this is the qubits, 0 and 1, 0, and then these are the classical bits, 0 and 1. So there's measure of 0 and 0 here. So this is saying we want the 0th qubit, this one here, and we want to store the result in the 0th classical bit here. Similarly, the next element says the first qubit, and we want to store that result in the first classical bit. Okay, so I want to just point out one last thing, and actually this came up briefly last week. In Qiskit, or in IQX in particular, Qiskit will output the classical bits all sandwiched together. It uses the slash to say that we have more than one classical bit smushed together, put together. So they just use 2 lines instead of, say, 4 lines in this case, because if you have 2 lines for every classical bit, this can get very long, and there's just a better way to do this. We never apply gates. So the slash here just says, hey, we have multiple classical bits. and the number tells you specifically how many. So 2. So long as you feel comfortable with your code, for the most part, you can ignore this part. But I just wanted to point it out. Okay. The most important part is this as the takeaway here. Do we have any questions so far? Any questions? Okay. Let's look at a different one. What would we have to do here? I'd love to see in the chat, or if you want to unmute and speak up, what do you think? What would we see here? In other words, what commands do we have to use with measurement to get this result here? Assume that the gates are already applied, everything is already done. What is the one line of code we need to measure in this way? What do we think? Go ahead and share in the chat or speak up. Okay. Seeing some different things. Yes, there is one way so that you can measure all the qubits. This way is a little more flexible depending on what you want to do. Again, you may not always want to measure them, so we'll stick with this. But it of course, if you are measuring all your qubits, that is fine too. Yeah, beautiful. It's no different, actually. This is the same as what we've been seeing so far. So we have our gates and everything, but it actually doesn't change as far as the measurement is concerned. We measure the 0th and store the result in the 0th classical bit. Similarly, we measure the first qubit and we store the result in the first classical bit. Because we've smushed all these classical bits together, Qiskit just provides you a number next to it that says, hey, by the way, this is classical bit 1, or previously this is classical bit 0. Okay. Now, how about this? This one looks a little different. I'm curious, what do you think? What is the command? So again, I'm looking for an answer like this. QC equals measure of what? What do we think? What is this one? Take a minute to look at the circuit. It's okay if it's not obvious immediately, or if you're still confused, but give it a try. What do you think? Share in the chat. Feel free to speak up. Ooh, okay, seeing some different answers. So it's always that list where it's totally spot on about that. Question is, how does it change? Or does it? Yeah, nice. So in fact, this one actually is the same as before. It's still the same thing, which might be a little shocking because it really doesn't look that way. But let's walk through what's happening here. We measure the 0th qubit and store it in the 0th classical bit. That's what's happening right here. So it may happen after the other one. Measure doesn't specify the order necessarily. It just says, hey, by the way, at some point, measure the 0th qubit, store it in the 0th classical bit. So that happens here. And then measure the first qubit and store that in the first classical bit. This is good and bad. What's happening here is because we have one fewer gate here, the first qubit is basically done right away. So Qiskit plays this kind of smart game to try to push everything together and slides it under here. Because a quantum computer can run gates or operations on different qubits at the same time. That's no problem. And so long as there's nothing that qubit 1 has to wait on, it can just measure right away. That's no problem. Whereas qubit 0 has to have the X happen first, according to this diagram, so it needs to wait for the measurement. So you can imagine this is kind of like slot 1 or column 1 here is what is the first thing we do. Column 2 is the second thing we do, so on and so forth. So this is more of just a heads up. You may notice things getting squished in different ways, but from a coding perspective, it's actually much simpler. Okay, so it's actually much simpler. go ahead and work on this example. Go ahead and work on this example now, or actually, I'm just going to go ahead and show you. So this is the result here. I'm going to go ahead and show you because this is newer for us. But here, if we want to store multiple qubits, more than 2, in fact, we can do that. We just need to specify the index. So 0, 1, 2, 0, 1, 2. The 0th qubit stored in the 0th classical bit, the first qubit stored in the first classical bit, and the second qubit stored in the second classical bit. So when we want larger circuits, we can measure no problem. It's really no issue, and this way is very general. Okay. Lastly, and we're about to get to some exercises. I want to make sure you get a chance to code this up. Lastly, the results come out as 1, 0, and 1, 1, for instance, if you have multiple qubits, but it may be a little confusing. Well, which one is the 0th qubit? Which one's the first qubit? The important thing to remember is they are ordered from right to left, or in this case, almost kind of top to bottom. So if you have the result 1, 0, what that is saying is that qubit 0 is 0, the first one here to the right or the top, and qubit 1 is 1. And then of course, in this example, they're both 1, so it's a little easier. Okay, that can be easy to get tricked up on. Just try to remember it goes right to left or top to bottom. Okay. Now let's move to the exercises, and here we'll be able to see some answers to our questions. In particular, exercise 1 is to create and draw a 2-qubit, 2 classical bit circuit with no gates applied, and then a measurement at the end. So we've already created the circuit for you, but now we want to measure. QC dot measure 0, 1, 0, 1. So this is the same kind of thing we've been seeing so far. This is in fact how we created the visuals on the previous slides. Okay, I want to stop for questions. I notice there's some, what is the difference between 0, 1, 0? Yes, so Amar, if you change the order, it doesn't matter so long as you keep the ordering consistent. So 1 goes with 1, 0 goes with 0. That's a very good question. Okay, let's actually run this. So we get 1,024 results out. It looks awfully similar, but notice that now we have 0, 0 as an outcome. Okay. Now exercise 2. Let's create and draw a 2-qubit, 2 classical bit circuit with quantum gates applied in the order below. So we've actually provided the gates this time, but we want to provide the quantum circuit now. So quantum circuit. And here we have to specify that we want 2 quantum bits and 2 classical bits to store those results. Then here we want to measure. So we create our circuit, we apply our gates, and then we measure at the ends. But we have to say from 0 and 1, we want to store in 0 and 1. And we get this result out. Again, Qiskit will move the measurements around to try to pack it in to the neatest space, but no need to worry too much about that. And we can run, and we get a 50-50 result out with 1, 0 and 1, 1. So this is a superposition with multiple qubits. Okay. Now, lastly, we want to create a 3-qubit, 2 classical bit circuit, so different numbers of bits, with gates applied in the order given below, with a measurement of just qubits 1 and 2 at the end, and then we'll simulate. So there's a lot going on here, so I'll walk through a little more slowly. So first of all, we want to create our quantum circuit, and we've been asked to do it with 3 qubits. Qubits come first, and then 2 classical bits. So 3, 2. So again, these numbers do not have to be the same. Now, nicely enough, the gates have been already given for us. And then we want to complete this line. But here, there's also a small difference that we want to measure qubits 1 and 2, as in not 0 and 1, not 0, 1, 2, just 0 and 1. And then we want to store, or sorry, 1 and 2, as I just said we're not doing, 1 and 2. And then we will store that in classical bits 0 and 1. Now, this is a difficult problem. It is okay if this one does not make as much sense to you, though I encourage you to look back over it. And then we can run this. And in fact, we get some nice results out, another superposition. Okay, any questions so far? Any questions so far? Okay. So for sake of time, I'm going to leave you with the next two problems to work on your own. And again, solutions will be provided, but they will look very similar to these ones. They're really not that much different. Particularly the first two are perhaps the most important ones. The bit I want to make sure we get to is the C naught gate, is one word for it, or the CX gate. I want to make sure you at least know how to apply it. We'll have plenty of time to use this and get comfortable with it. Trust me, this is a very popular gate. So it's okay if it's not making sense now, but I just want to make sure you see this syntax, how we actually write this, CX of 0, 1. So I just want to show you one exercise together, and then we can go through and practice whatever you would like. So I'm moving ahead now, pardon for the skipping ahead, but I just want to make sure you see CX here. So here, in exercise 1 of part 4, the CX gate, we want to create and draw a 2-qubit, 2 classical bit circuit with the CX gate applied such that qubit 0 is the control bit and qubit 1 is the target with a measurement at the end. There's a lot going on, but let me show you what this looks like and walk through this with you. So I'll zoom in here. So what I am saying with this line of code here that I've just added is I want the controlled X, the CX gate, with 0 as the control bit, the one that controls whether we do anything, and then applied to the first qubit. So this is the target bit second, and the control bit is first. So control bit is 0, target bit is 1. And then we have our measurement just like before. And we get something like this. Notice now that this gate actually combines both qubits, right? This is a true 2-qubit gate. And then if we simulate the results out, we get out 0, 0. Okay, so it's not a very interesting result, but we will start to be able to see interesting results because while a Hadamard is crucial for superposition, CX is a crucial one for entanglement. In fact, if you want to, you can go ahead to some later ones where you can create entanglement yourself. But okay, we've reached the time, so I will stick around to answer questions, but I don't want to run over. I know we moved a little quickly there, but you'll have plenty of time to practice. Remember, you have the Qiskit cheat sheet to look at. This is linked in both the lab and the homework, so you can always refer back to this. This includes the bits that we just went through with CX. It includes the measurements, including multiple examples. So rest assured you have access to this. And you can always look back over. Okay, so what I'm going to do is, great question. I will share the attendance code. The attendance code is 6485. Wonderful. I'll stick around for any questions, but please feel free to go and have a happy November. Happy November. So yeah, I will stop sharing my screen. Happy November. Have a lovely week, and I will see you all next week. But please feel free to stick around. And yeah, I do want to say, if you're feeling overwhelmed, that is okay. I know this went fast. I know this is a lot. We are going to keep looking at these things. We're going to have some more review time coming up soon because we know we've thrown a lot at you. So please do not worry. You will have time to catch up, to catch your breath. This is complex stuff. just hang in there and keep trying your best. That's all we want you to do. Just try your best, and I promise we'll all get there together. Okay, have a lovely week, and remember there's the homework assignment. I see some folks asking about using mobile phones for the homework assignment. That is a great question. I think I am not sure off the top of my head, so I don't want to waste your time. But this is a great question. So what I will do is I will reach out to the administrators just to see what their suggestions are, and I will get back to you on that, or see if they can put something out. But your best bet is to look at the student guide to see if there's anything in there for you, the student guide, and to or to email the student at Qubit by Qubit account. So